when Austrine asked me to make this presentation, I was thinking as a physicist, and I changed a few slides yesterday, saying it was a bit too complex. But I have additional slide at the end if we have time. Okay. So will be. You can ask any question. You can interrupt me. Anyway, I would like to thank ENHANCE to make this presentation, and I will talk about Raman, but I will start by the basics because I know that there is some electronic engineer, and so you have to remind some few stuff. So I will make a very short reminder on chemistry, seen by a physicist, more on condensed matter, vibrations, and then what is the optical process that you can find in matter, and we'll talk about weather forecast, and then we will go to what I changed yesterday is classical Raman, and a few examples that I may say I try to fit to the topic of this school. So basically, if you look at chemistry, yesterday we have some talk, so I will not go to the complex ligand theory, but just say that if you have two atoms that can bind, they will form levels, okay, depending on the electronic structure of one to the other. And you will have bondings and anti-bondings levels. And this is completely electronics effects. And if you now are able to put a chain of atoms together, you may form a conjunction bond and a valence bond. And in this talk, I will talk only about materials that have a gap, no metallic. That means you have here it's full and here is empty. Basically, it will be the limit of what I will talk about. And so this is basically an imaginary chain, and we will see that we can go to a solid, but it will not be treated. So now let's go back to this gas molecule. And so let's imagine that you have your lowest energy level here your highest energy. You may know that you will have some vibration, but in fact, if you shine light, you will have several processes. If you are in the RF range, you may rotate these molecules. So it's the principle of microwaves, or it's the reason why cell phone doesn't work on all bands of the gigahertz and megahertz range. Then we will talk basically on this kind of vibration. That means you have an electric field, and this electric field will move the molecules. And if you go too high in energy, what you can have is to break the molecules. Some people talk about that yesterday about CVD. You can break some molecule with some light. In nature, it's a principle of fabrication of ozone. So, and Raman will be a way to that is not. It's in between infrared and the absorption levels here. And so what you will do, you will send some light here. And so you will be in the transparent range. So basically light should cross the medium. But in fact, to have some process, you will need some nonlinear effects, which is basically the Raman, and we will talk about that. But before, I have just to go back to what was these vibrations. And so if you take a diatomic molecule, so I should have painted this in another color, but and I consider that okay, you have your electronic clouds that fix in fact, the two molecules can oscillate one to the other. It's a very simple case of harmonic oscillators that is very used in physics. And what you describe is the movement of these atoms. And what you found is that it's basically quantified by some vibration. I go very quickly on this, but what I may say is that the energy of this level is quantified and is proportional to the constant and inversely proportional to the mass of the atoms, or to the reduced mass of the atoms. So basically, yesterday some people talk about graphene, and so when you look at graphene, first, let's say you have, before graphene, you may say you have diamonds with sp4. And if you talk about graphene, in fact, it's missing one link. And so it's in the plane of your graphene plane, and what you see is one molecule. And so what you have is from here to here, you increase what we call here the elastic constant. And for example, if you bond here a carbon to something else, so it's not ended, it's not finished liaison, but I may say that you, if you decrease, you increase the mass of the bondings, what you found is that you expect that you decrease the frequency of vibrations. It's really general. If you now take more complex molecules that you take, for example, CO2, you will have, so it's a linear molecule, and you have several kind of vibration, which are bendings, or stretching, and so on. In fact, you can calculate the number of modes that you expect. So if you have only one molecule, in fact, you don't expect any vibration. If you have a diatomic molecule, you expect that you have 6 coordinates. And within this 6 coordinate, 3 can describe the translation of this molecule in the atmosphere. After you have 2 rotation, and this one, okay. And after you have 1 vibration that I describe here. And you can extend that to linear molecules to some relations that if it's a linear molecule, you will have 5n the number of atoms in the molecule minus 5, which is a 5 here. And if it's a nonlinear molecule, you have an additional rotation, and you have 3n vibration. Okay, so now we have seen what is a vibration in a gas. I will just go to solids, and I go back to the chain I described before. And so now you imagine you have your chain with some electronics that bind everything, and you may found 2 kinds of vibration in this chain. So it's a textbook example in physics. So you have a longitudinal vibration that make movement like that between the atoms. So this longitudinal vibration are the same that you found in sound. And additionally, you have in solid, you have transverse possibility that you can also move up and down the atoms. It's really descriptive. I don't want to be more complex, but if you have a diatomic structure, what you found is you have this longitudinal and transverse possibility, but also you found that you have not only acoustic vibration like air and when I speak, but you have higher level due to the number of atoms. I have the finger. And you have this additional atom levels here that is you don't see in fact except in infrared and Raman. Okay, so in fact this is a model. The real case we talked about yesterday, zinc oxide, which is a Wurtzite structure. So you have now you will not consider the molecule, but the unit cell, you have 4 atoms by cell. So what you expect is 3n degrees of vibration. And so if you remove the acoustic branch, you expect 9 optical modes. Okay? These modes are here. So I take some time. You have A mode here. It's A and B, it's symmetric. It comes from irreducible representation of the vibration. So one is vibrating like that, with atoms like that, and the other like that. It's one degenerated because it's along the z-axis. B1 and B2 is the same, is also only one degenerated. And after you have 3 E modes that can vibrate in 2 directions of the plane. So they have 2 degrees of degeneracy, so you can count 1, 1, 1, 2, 2, 2. It's make 9 modes. Okay? That was just vibration without motion. If you add now the lattice structure and you add the next neighbor interactions, what you found is it's much more complex dispersion than the textbook case. Okay, the reason is that you have the next neighbor, you have many things going on, and the only way to solve this is now by computing. You can observe few dispersion branch by neutron scattering, but you have a limited resolution in neutron scattering. And really the best, and now the technique of ab initio calculation are great and can predict really well as what you expect in the dispersion of all the mode. So here I put brilliant zones. It's because what it represents here is specular point in the reciprocal space. So you don't describe this in time scale or time-dependent vibration, but in the K space. Okay, is it okay for that? Okay. Okay. So now I go back to the optical. So I say Raman comes from optical and laser. But first you have to imagine one of the very important points in optical processes is energy conservation. And this is a very, very strict effect that if you send light, you have a conservation between reflection, what is reflected, transmitted, and absorbed. Okay? But some people who have turned on the heater knows that, not the cooker knows that it can also emit light, okay? In fact, the Kirchhoff law says that absorption and emission should be the same, okay? So basically that is at one wavelength, but the equality is considering all the wavelengths, taking care of linear process, non-linear process, conversion modes, and so on, okay? Its effect, its vibration, and it's also some radiativity. So now we go and we will apply that to a complex case that Professor Matur wants to discuss today. It's the weather forecast. So if you look at conservation of energy, you have the solar cell, you have some emissivity of the Earth, you have many processes. This problem is very, very complex, but still you can apply this. But you have to apply a lot of other nonlinear equation of hydrodynamics, thermal, and so on and so on and so on. But so I will not talk about that, but I will talk first to another more simple case for physicists is why the sky is blue. And so everybody have seen this picture of you have on the sunset, you have a blue sky, and when you go, you have a bit of green here, red here. So there is no secret on that, okay, you have the sun, when on the sunset, that the light crosses the atmosphere, and so the blue light is first diffused after the green, and the red is almost not diffused over 200 kilometers, something like that. And so it explains why the sky is green. But what is also interesting is that this light diffuses in all directions and also changes the polarization. This effect is called a Rayleigh effect. We will come back to this effect. The Rayleigh effect is an effect that increases in the blue. Okay, we will see it's depending on the wavelength over a power 4. And after, it depends on the size of the molecules here, or the cross-section of the molecule, I would say. And so this effect is visible by this effect in the sky. And if you look to the CT, you will see the CT are usually gray. It's due to me diffusion. And if you look at the clouds, you see it's white. And also it's a change of light direction. But this effect is not colored. Okay? So I talk about that because it's very important to say that this is a change of direction of light. And also polarization. But you don't change the energy of light. Even if you change the color, you change and so we call it elastic processes. Okay? So now we will go to more complex stuff, which is inelastic. And the first inelastic process was predicted by Margueron a few years before Raman. He was studying vibration in solids and say, okay, if I have a wave traveling in a solid, so this may create a diffraction pattern. And if I send light on it, this should diffract the light. And at this time, they didn't have the way to experiment that, okay? But the idea was there that you send light and you have a traveling wave. It's important that it's traveling. The reason it's traveling that you have to use another thing, which is a Doppler effect. The fact that when you have a velocity, so you will have a change of frequency, okay, between sound, you change the frequency. So this is not a nonlinear effect strictly, but in fact what you see is that if you send light, you will have a diffusion, scattering, that have a wavelength that is different due to Doppler effect. So basically what we are looking at is here, we are looking at this low vibration, which are in the gigahertz range. Okay? It's important again to say that it's a traveling wave, and you have conservation of energy, so you can draw the impulse of the light coming, outside light, and your vibration is like that. Okay. If you look, it was much later, I don't remember exactly, that they observed the first Margueron peak. So here you look around here. So you have some Rayleigh, we see the Rayleigh in the sky. And also you have additional peak here at few gigahertz, 10 gigahertz, something like that. So what is important in this phenomena is that it's a very nice way to probe mechanics of materials that you don't know yet. And you can use and ask to specialists to measure the vibration property of this new material in thin film, in nanostructure, and so on. It's not so simple because, in fact, I say it's a traveling wave that modify, in fact, the index of refraction, and the index of refraction is included in the calculation of the Margueron shift. But anyway, it's a way of measuring properties, mechanical properties, very powerful, but you have to think that you have some dispersion and it's not exactly the 0,0 so at the Young modulus it's a bit bent to this value. Okay? So it's an inelastic. You have a change of direction, polarization, and you have a change of energy. Okay, Now let's go back to my picture here. And I say I send some light here. And what was interesting is that it was observed before Margueron, and it's why Margueron didn't have the Nobel Prize for that. It's because in Nobel Prize you need really to observe a phenomena. And this is the case of Raman. So it's who basically sunlight. It's so at this time it was in 28, 29. It's sunlight. So at this time, the way to sunlight was to use the sun, or to use some plasma lamp. And so what they use is many filters. They put a liquid at this time. It was a liquid of benzene or something like that, and look at the emission of this liquid. And what they observed, that they didn't observe the Margueron, of course, but what they observe is some peak very far away from the relay mode. And this corresponds to the optical mode that you can find here. This is the mode that I say come from that you have many molecules and you have additional level at a higher energy. So this energy is above terahertz, few terahertz, okay, from 3 to 10 terahertz. Okay. Again, you have conservation of moment and conservation of energy like in Margueron. Okay? But there is a big difference with Margueron. You remember I told you that Margueron corresponds to a traveling wave. But if you look at here, it's stationary. Look, this is a k vector against the pulsation. This gives you, in fact, the speed. Okay. Light speed, or light cone, is here. And this is a representation of acoustic. And so what you see here, that is flat. And it's always the case in Raman. On the center of zone, it's always flat. And so the mechanism of Raman is quite different from Margueron, where you have this traveling wave. And I will give you a classical explanation of that. But we can talk about later of more complex story. So basically, you have an electric field that go to your material. So what it does, it moves up and down the electronic clouds. And so this excitation wave can be described by a polarization, an amplitude, and a propagating wave going to your material. Okay? So in the next page, I will say that I am looking at this point. So in z equals 0, for example, as a reference. So you will not have this term. And I will say it's in phase at the beginning. And so I will have this electric field. So the clouds move. And so you have an induced polarization of these clouds. That is the susceptibility. So it's related to the index of refraction and the electric field you applied. It's a linear response of the material. Okay, now do not forget that we have a solid. And so what you do is you move the clouds everywhere. And these atoms are linked also by this is the clouds of electronics, but here it's a network of the nucleus. And it doesn't vibrate at the frequency of your electric field. What's happened is that it will vibrate, but at a much lower frequency, which is what we just saw, the vibration modes. So here is the frequency of your light. Here is your dispersion of acoustic, for example. I take any example. And so what you have is you say that you will couple these two. So you will make the product of your electric field and your vibration. So how you do that So this is the electric field. This is your vibration. And so what you do is you will have a product of your electric field and your vibration. So it's not enough if you just do that. What you have to consider is that, okay, if I say that the atom vibrates, I have to say that you have some susceptibility change at low frequency. And so what you do is a small development with Q vibration. So it's, I skip a bit the complexity, but this is a proper vibration of your system, okay? And I assume that you have this, for example, vibration, which is the first vibration that we see, for example, for inverse height, oscillating at a frequency omega, okay? Secondly, you have to think that it's possibility that it's a traveling wave, okay? I say it was a case in Margueron. But then if you do that and you keep K here, you will see that we will see back that it will not work. So let's drop this term first. We say that we are in the long wave. That means long wave, the wave length is inversely proportional to the impulsion. So we say that the impulsion go to 0. You are on the center of the zone of the Margueron zone. And so now you have your modulation of the susceptibility by the vibration here, and you apply the electric field at high frequency. Using simple trigonomic, I can make that in class, but you develop this equation to a first term here that is only oscillating as a vibration of your electric field. It will be the Rayleigh scattering. And after you have a product of the vibration of your mode and the vibration of the electric field that you will develop in two terms. And this will not be 0 if you have the frequency of the beam, and scatter beam, in fact, equal to the vibration of this one. So this, no, in fact, is not exactly that. You will have a vibration at a frequency here minus 1 vibration, or at a vibration plus. So Stokes means your energy is at lower energy or higher, higher wavelength, or anti-Stokes, it's at higher energy. So what is important is, I told you just before that you will have to consider that Q is 0. Because if you put a Q term here, you see that you will never have this cancellation of terms. And this is really important, that Raman scattering is at Q equals 0. Okay? So you will have this modulation and some polarization emission. The fact that it's a classical theory that we didn't describe what was in this term of susceptibility. We have not the magnitude of that. In fact, it's 1 particle per million or billion that will be scattered. So when Raman made his experiment, the first experiment, he waited several days with photographic plates just to have some blurred spectra. Okay. So so we didn't describe, but it will be helpful for it will be enough for us. And so what you have also, we didn't describe also the temperature effect and what is the effect of temperature. So it's not included in this classical theory, but anyway. What is important, that is described well, that it works at the center of the Margueron zone. And so that means it's a long wave phonon that is not propagating, that they are stationary. Okay. Okay.
So now maybe I should, I will skip that. But I will just say that, okay, this term of susceptibility describe in fact the clouds, okay? And in Raman, if you are Raman active, that means you have a change of the susceptibility that is not going to, that is not flat here. At the same time, you will be Raman inactive, and so on. This is for all particles that have a center of symmetry. Ferroelectric have no center of symmetry. We will see, and it's why I want to accelerate. That's if you have no center of symmetry, this exclusion rules doesn't work. So that means if you do infrared, you will not see the same modes as in Raman, and reversely. Okay, so it's a complementary technique. Okay, quantum field will describe you that it's a bit more complex. You have virtual levels, and you photon propagate, interact with a medium. Okay, you know that waves are propagating in medium from point to point. And so you have a loop, and you can exchange during this loop a phonon. But, okay. Now let's go back to this important thing is that we say that there was a term of susceptibility here. So what you say, we excite with a light coming from some point with a K incident, some polarization. This is your medium. What you have to consider now is also that you will diffuse light, and so you also consider the scatter, the polarization scatter, and so it's a projection of the two. In fact, it's a fluctuation dissipation theorem behind, but what you have is you can reduce that to a simple fact that this is a second order tensor because it's a dielectric. And if you want to describe this experiment, you just need the incident, the polarization of your light incident, the polarization of your scattered light, and the polarization of your in the wave vector of your scattered light. And so what you got, so this is your susceptibility. This is the mode I described before. This is a tensorial representation of this. It's a matrix representation of this tensor. So basically what you say is, for example, if this, so for example, if I come from x direction, that means I put x incident, I arrive along the x-axis of your crystal. I have two possibilities for the polarization, y or z, you agree? So I can be in three cases. I can look and polarize, excite with polarization along y and look at the polarization along y. Or I can move it to 90 degrees. I can also do this effect, but it will be the same. Or I can look at the crystal by two directions of polarization along z. So, for example, this is a case. So the black one is x, y, y, z, x. The blue is x, z, z, x. And this one is a cross polarization of the two polarization. And it's the same to be like that or like that in when you have not a magnetic or resonance effect. Sorry. And so how now you calculate which mode you're expecting? So you look, for example, I arrive along x. So I cannot see this direction. And so I look only this term here. And so if I arrive along x, I can see here yy or zz, and this one will be not existing. The same here, it's only cross polarization. Here I cannot see this mode and so on. I can see only along yy, and here there is no. So you can see what you expect in Raman scattering just looking at that. If you look at reality, it's a bit more complex. More complex means that, okay, I will not go to the details, but I can tell you that all what I say is predicted. You expect that here, for example, an XZZX, you expect E2 mode and A1 mode. But if you look, you have other mode. And here you have another mode. It's because this is a ZNO on a sapphire substrate. So first of all, this star is a substrate. It's a sapphire. So you have to take care of that. But also you have big bump here, which are what we call second order mode. And I just want to introduce that. It's the fact that, okay, I tell you before that your dispersion of light is like that. And I only see zone center mode here. But in fact, if in the dispersion you have another flat area like that here, it means that you have a high density of state here. And it's possible that you can see this. It's possible. Especially if you have two phonon process. And this is a second order process. And so you difference first order to second order by doing temperature variation and so on and experiment. But anyway, so if you do Raman, you can have surprise that is more complex. Okay? Okay, now I will go to the example. So I have 20 minutes, so I think it will be enough. And I will start to say that usually when you go in a lab, except in some physical or chemical lab, you will do some what we call backscattering. That means you have a microscope here, the light goes through your sample and come back. Okay. By the way, it's very shiny because there was no much light, okay, in the room. But and also usually we can say that because we use an objective, okay. If your material is not too diffusing, okay, it's less dangerous than using a focus beam. So for the people who are doing some Raman, don't be too much scared, except if they put too much power, that the scatter beam will not kill you because it's diverging. Okay? Just, but I don't say that it's not dangerous. But I say just it's less dangerous when it's not focused. When it's focused. Okay? Anyway, so you have several geometry. You can polarize like that, polarize two like in the other direction, or cross the polarization. And the only thing you remain to you is to turn the sample around. But you see that you will not have some effect like that because you are only looking back and forward. Okay, so before starting, I will talk about film technology where we apply Raman scattering in film technology. It's mainly film that was done by Osrin. But I would say that first, before doing Raman, you have to do some diffraction, okay? Raman will give you many information, but you may need first diffraction, okay? To know if your film is its texture or epitaxial and so on, that Raman will never tell you, okay? What you will look for is some correlates some effect, and to be sure that what you see in diffraction is well a stress effect. So you can correlate it if XRD and Raman and say, okay, the two techniques tell me that it's a stress effect and not just diffraction, but there was some other chemical effect that make it the mode shift and so on, and it's not only stress. You can look also some composition disorder, and also I will talk about a bit of twinning, okay? And okay, if you just make theta to theta diffraction, Raman look a bit more generally all. You don't need diffraction rules. Okay, you will see a bit all. So it can be sometimes very interesting, and for some of our students just use Raman as a very quick technique just to look if there is some parasitical phase. And this particle phase, for example, cannot diffract because they are not in the correct plane to diffract in theta to theta. Okay. So anyway, so let's start by our enemy, lead titanate. Okay. 10 years ago, we were working on lead titanate. So now you say we switch, but so what you want to know is, okay, you have the group symmetry that you can find in tabulation. Okay. You go to, for example, Bilbao server because you are not good in group analysis. You enter in the number of cells, the lattice parameter, and many things that can be interesting. And what you see is that you expect 15 modes. We know that it's 1, 1, 3 by 3 degree of freedom, it's 15 modes. But what is interesting is that you will also have the symmetry of mode, which is more complex to calculate by hand, but it can be. So within this mode, you will have 3 acoustic modes. So I remind you, this is 1 and 2 degenerated. And after, you have your Raman and infrared. So both are active because I say there was a break of center of symmetry. It's a ferroelectric. So they are both. And here, you have 3, 1, and 12. So mode. I don't use Bilbao server. I use a program developed by Glazer in Oxford. But anyway, it's the same thing. That Bilbao is better, but have some.
The break is free.
Yeah, you can download favorite. And you will have plenty of things. But what you have, it's nice, is that you enter the CIF file format of your diffraction, and it gives you everything. Anyway, okay. So our enemy is here. And there is a thing that I didn't talk. I will go very quickly, but I may say that, okay, it's a polarization, okay? And so I may say that I didn't talk about transverse and longitudinal mode. So it's a bit complex for few, but anyway. For example, I will look at this configuration. You remember, I arrive along Y, and the polarization is along Z. So I arrive along Y, and the polarization, for example, is Z like that. And I diffuse along X, I assume it's this direction. And I have the polarization here. In this case, what I expect from Z, Y, I expect this amplitude of mode. So I expect E mode. Correct? Yeah? Okay, the polarization, okay, I expect this mode. But if now I look at this table, if my propagation is along Y, and I look at E mode, I will see a LO mode. It will be a longitudinal mode. You see that Y is along Y, so it's longitudinal. And when I scatter X, okay, I will be along X. I look at E mode here, Y, EY, and I have a TO mode. And so now, if I look, so this is made in different geometry, okay? It's not single backscattering. If I look here, Y, Z, Y, X, Z, X or other direction, what I see is that I see E mode. So this is all the spectra possible to have on a single crystal of lead titanate. Okay? All the configurations that you can expect. Sorry, it's not very beautiful, but I did this picture 10 years ago and don't have any more spectra. Anyway.
Excuse me, but the shift is because of local distortion?
No. The shift is because a PowerPoint cannot make you the line where you want. No, it's a single crystal. Okay. Eventually we can talk about twin. Okay. So it's a bit complex, but if you make a phase field modeling of ferroelectricity with stress, what you expect that you will have for epitaxy on different substrate, you will have a configuration of domains. Okay? And different domains depending on the lattice parameter of your substrate. For example, you can have C and A domain here. C domain, that Z is like that, and the other is in the plane. Or you can have A1, A2, but they are in different directions. This is what we call twinning in ferroelectrics. It's very, very important phenomena, in fact, in thin film. Even when you are developing eBacuo, supraconductor, and everything like that. It's a very, very important phenomena. Anyway, if you look back scattering, you will have the possibility to make on the surface, on the edge, you can change the polarization. And so if you look at spectra, for example, grown on lanthanum nickelate, aluminate, you will see spectra that are shift now. Okay, they are shift. The spectra are shift here. Okay, but in fact they are not shift due to stress and so on. It's because you light go, you have some ferroelectrics domain, and what you do in this ferroelectrics, you couple light to the polarization of your ferroelectrics. And so what you have, if instead of having a mode at a certain frequency, you couple light, and so it will shift with the angle of the piezoelectric effect, which make ferroelectrics very complex to analyze. Okay? Anyway, I switch that to say that it can be very complex to analyze. Now, so we are not interested by lead tantalate. So let's look at another material, for example, strontium titanate. Well, I don't know if strontium is better, but anyway. And it's not very interesting. Why? Because at room temperature, it's a cubic material. And so you have to go to very low temperature to have a ferroelectricity. Some people did some ferroelectric film stressing them at room temperature. But Giacomo will tell you that if you have a thin film of few nanometers, you will not harvest a lot of energy. So it's a bit a problem. So barium titanate, it's a good idea. The problem is that near temperature, there is plenty of phase transition. It's not very stable and so on. You can always add some stuff inside, huh? But it's not it's not our candidate. And our candidate is lithium niobate. Oh, okay. So lithium niobate have a very high Curie temperature. Some people in the 60s thought that there was a soft mode. It's not really a soft node. You see that the line, you have few points, and after they collapse. So it's not a soft mode because, in fact, if you look, there is no structural distortion. Okay, you just move a bit, so you have some distortion, but also you have a second order phase. Okay, it's okay for that. 5 minutes. I have to stop. Okay.
No, you.
I can continue.
Concept here. Yeah, I think it's important.
No, but it's cool, but it's finished. No. Okay, no. No, I have a few others, but it's too long. I mean, I think I have 10 or more slides to go, so I think maybe I can go quickly, yeah, but sure, say that, okay, I just want to talk about stress in thin film. Okay, you have two ways to have stress, basically. Two ways to okay. What you have is you have a thin film, okay. So this is a elasticity of your film, okay. This is deformation against stress. So when you deposit your film, you can have formation of epitaxial stress, okay. So you start at some point here at some temperature, which is not exactly the room temperature, okay. And so when you cool down, you will relax some energy, but you will still have some energy in your film. Some energy can be relaxed inelastically, creating domains and things like that, cracks and things like that. I hope no for you, but it can happen. But you have some store energy. And basically, when you do diffraction, X-ray diffraction at room temperature or Raman, what you look is what is this stored energy in your film. Okay? You don't know what's happened here. Okay? Except if you do high temperature diffraction in situ and so on. But anyway, not always, and not everybody do that. And so at the end, what you have, if you look at a thin film, you can have twinning, so follow well the crystallographic directions of your lithium niobate for z-axis along sapphire along z. But if you look at other film, it can be very nice. It doesn't mean that there is no stress and there is no problem, but it looks like nice. Anyway, so you can look at composition by Raman. So look at the phase diagram. So we worked on that a few years ago. We can look at temperature effect. So I told before that Raman depends on temperature a bit. You can look at, so I talk about stress, you can measure the shift of Raman. What you have really to think is that if you take an oscillator and you move your atoms, if it's a harmonic oscillator, it doesn't shift. What you have to think is when you pull your oscillator, your constant, elastic constant, is not linear. It depends on the stress you apply. It's the only way to imagine that there is a Raman shift when you strain your material. Anyway, so we work on that a few time ago. We calibrate the stress effect on Raman mode of lithium niobate. It's very long and you crack a lot of samples. But at the end, for example, we found that in lithium thin film, we have one mode here that shifts a lot with stress. In fact, you look, it's two modes together, and it's probably that there is a repulsion between the two that explains that it shifts a lot, because all others shift very little. Anyway, I will finish here. I will finish on disorder effect and say that, okay, I tell you that Raman, you look at the center of Brillouin zone, okay, but if you have disorder, you break the translation symmetry. And if you break the translation symmetry, this will flatten, okay? And so you will have a mode that is flatter and flatter. And if you go to the extreme case, okay, what you will see in a glass, you will almost see, without considering second order mode, you will always see the density of state of phonon in your material. Okay? I hope it's okay. 1 hour. There is few more if you want. No.
I think
what? During lunch for the one who wants.
If you want, you can click 5 minutes. I think it's because it's if you want to show something.
No, I mean, no. Okay, I can show. No, I will. Okay. I will just finish that. Okay, in lithium niobate thin film or material, you can, using the width of mode and the thing I saw about disorder, you can really characterize the stoichiometry of your film, and really precisely. This is very interesting. And I will conclude on one point, is that you have very little scattering. And you have also to think that lithium niobate, okay, have a light element which is lithium. And most of the people who look on lithium know that it can migrate quite easily. And for example, if you use UV scattering to look close to the gap or in the gap, what you do is during your experiment you use lithium in your film. And so it's nice because usually we want to go to the UV because we increase the light scattering, but at the same time we are destroying the film. So there is no way to wait a long time to make Raman scattering. So it's a beautiful conclusion. And I have other application, but it's the end, and I think I cover a few aspects of ENHANCE project.